Hello and welcome to this presentation related to friction belt drives. This is part 4 in the lecture series, and in this particular presentation we're going to consider further friction belt drive questions. It's strongly recommended that you've reviewed the previous 3 parts to this lecture series, as they contain underpinning knowledge that is not recapped in this presentation. The presentation overview. We commence with example 5, which is an analysis of a rope and bucket used by archaeologists to extract artifacts from the bottom of a well. This is essentially the analysis of a winch and used as an illustration of how to apply flat belt theory in a different context. Then we have questions extracted from our notes. Question 5 relates to a vee-belt, where we consider centrifugal effects. We have to determine initially the power that can be generated by the given parameters in the question, and we also have to determine the maximum power that can be transmitted if the belt drive is operating at optimum conditions. Question 6 relates to a flat belt with no centrifugal effects considered. In this case, we have to calculate the belt tensions, both the tight side and the slack side tensions, and given the information in the question, this will require us to generate 2 simultaneous equations to solve for TT and TS. The full work solutions for example 5, question 5 and question 6 are included within the presentation. You're left with question 7 to review at your own pace. This relates to a vee-belt, where we consider centrifugal effects, and we have to determine the power that can be transmitted given the parameters in the question and the initial belt tension T0. Question 8 relates to a flat belt with no CF effects considered. In this case, we have to determine the friction coefficient mu, so transposition of an Inderseal equation there will be required. And finally, question 9 relates to a capstan. We have to calculate the number of turns or revolutions of rope around the capstan. Essentially, question 9 is based on example 5. So here are the approximate start times for example 5, question 5, question 6, 7, 8 and question 9. Hopefully they will aid your ease of access through the presentation, but please remember they are only approximate start times. Let's consider example 5 from your workbook. This example is used to illustrate a different context in which the belt drive theory can be applied. So archaeologists are excavating at the bottom of a Roman well. A rope is wrapped around a horizontal cylinder located across the mouth of the well, as illustrated. This is a sketch of the cylinder showing it positioned across the mouth of the well here. An archaeologist on the surface exerts a pull labelled TS in our sketch here of 30 newtons to the free end of the rope. We're asked to determine the least number of complete revolutions or turns that the rope must make around the cylinder to enable a bucket mass of 10 kilograms to be raised from the bottom of the well. As the environmental conditions can be damp, we can assume a coefficient of friction of 0.15. The answer is shown here in the bracket. So to solve this problem, we're going to apply belt drive theory. So we refer to our summary of formulae from our previous presentations. This relates to flat belt drives. So what we're trying to find in the question, we're trying to find the number of complete revolutions or turns that the rope has to make around the cylinder here to allow us to raise a 10 kilogram mass if we apply a 30 Newton force. So essentially we have a winch system here where the effort can be considered to be the slack side tension. So that's the TS shown here, the pull of the archaeologist, and the load generates the tight side tension, and that's due to the weight of the bucket. Just be careful in the question, the bucket mass is given but of course we will need to calculate weight force, and that's effectively the value of Tt in our belt drive equations. So what are we trying to find? Well, we're trying to find the angle theta, angle of lap effectively. And what are we given in the question? Well, we're given the friction coefficient, the damp environment. We're explicitly given the slack side tension of the rope, and we're implicitly given the tight side tension of the rope, the Tt here, because we're given the mass that has to be raised. Let's need to be careful with our units here. So if we can find all the information with the dix, we can then rearrange the equation to find an angle theta. If you think you can attempt this question without further assistance now, I'd encourage you to stop the presentation and do so, but I will outline the full solution on the following slide. So here's example 5, the full work solution. Extracting the information from the question, we know that the TS, the force applied to the rope, is 30 newtons. We're given in the question the mass of the bucket to be raised. This mass here is 10 kilograms. So what we'll need to do is calculate the weight of the bucket, label it W here, which is the mass multiplied by gravitational acceleration, to calculate the tight side tension of the rope. So the mass is 10 kilograms. We always assume G to be 9.81 meters per second squared. So the weight is 98.1 newtons for the bucket, the mg. So Tt is equal to the weight is equal to 98.1 newtons. From the question, the coefficient of friction mu is 0.15. Then using our equation from our formula sheet, Tt divided by Ts is equal to e to the mu theta. We need to transpose that for theta. So this is effectively an indecile equation I'm trying to solve. And as a previous lecture on solution of indecile equations, if you will need a recap, essentially the process requires us to take natural logarithms of both sides of the equations. So effectively on the right hand side of the equation, the ln cancels with the exponential function. So we're left with mu theta, which is now shown here on the left hand side. And that's equal to ln of Tt divided by Ts on the right hand side. Dividing both sides by mu, we end up with theta, the angle of lap, is ln Tt divided by Ts divided by mu. Inserting the values for Tt, 98.1 newtons, Ts, 30 newtons, and the coefficient of friction mu is 0.15. So that evaluates for a theta value of 7.899 radians. Remember, theta is always in radians. We're using the belt drive equations. And all I've done on the next line is used a unity bracket to convert from radians into revolutions. So approximately 1.26 revolutions required. The question says state to the nearest revolution, so the least number of revolutions or turns of the rope around the cylinder is 2. So for your reference, that's a slight variation in the application of belt drive theory. Let's now consider more questions from our workbook. We'll commence with question 5 here. A 4-to-1 speed reduction between two shafts at 2 meter centers is provided by 4 V-belts running on pulleys mounted on the shafts. The effective diameter of the driving pulley is 350 millimeters and it runs at 740 rev per minute. The pulley groove angle is 40 degrees and each belt has a mass of 0.45 kilograms per meter. The coefficient of friction mu is 0.28. We're asked to calculate the power that can be transmitted if the tension in each of the V-belts is not to exceed 800 newtons. We're also asked to determine the percentage increase in power transmission if the belt now operates at its optimum velocity. So essentially there are two parts to the question. In the first part here, we need to work out the power transmitted for the given conditions stated in question 5. To answer the final part here, we need to now consider the belt running at the optimum conditions. That's when the centripetal or centrifugal tension Tc is 1/3 of the maximum belt tension Tt. We've reviewed these characteristics in part 2 of our lecture series. The answer for the first part of the question is shown here, and for the second part shown here. I would encourage you to start the presentation and attempt this question, although I will show you the full work solution on the following slides. And to help your thought process, here's the summary of formulae we used in previous presentations, and this relates to vee-belt drives. And for the first part of the question, we have to find the power transmitted, P, so I'll be using this equation here. And for the second part of the question, we have to find the maximum power that can be transmitted, so I'll be using this equation here, and noting that the centrifugal tension is 1/3 the maximum belt tension. So I would now encourage you to start the presentation and attempt this question, but I'll very briefly outline the full work solution on the following slides. So here's question 5, the beginning of our solution. Just remember we have 4 off vee-belts here, and the maximum belt tension stated in the question is 800 newtons, that's the Tt value. Just note for reference that the centre distance between the shafts is 2 meters, that's shown here, C is 2 meters. And note we have a 4-to-1 speed reduction, so that means if the drive-in or smaller pulley has a diameter of 350 millimeters or 0.35 meters, that's dB labelled here, then for a 4-to-1 reduction, the driven pulley will be 4 times the driving pulley. So dA labelled here is actually 4 times 0.35, so 1.4 meters. I'll let you review the other information at your own pace. Question 5, solution continued. Just repeated the 4-to-1 reduction speed ratio. In mathematical notation, the diameter of pulley A, the driven pulley in this case, is 4 times the diameter of pulley B, the driving pulley. You can calculate the speed of the driving pulley, omega B. We're given in the question the angular velocity in RPM, so I converted that into radians per second here. The groove pulley angle was 40 degrees, that would be 2 beta, so semi-groove angle beta is 20 degrees in this case. Here I've worked out the angle of lap on the smaller pulley, so theta B, evaluated it in degrees here and converted it to radians here. So 2.61 radians is the smaller angle of lap. Question 5, solution continued. We can next calculate the linear velocity of the belt, V. That's the angular velocity multiplied by the radius of the pulley. We know the angular velocity of the driver pulley is 77.5 radians per second. The diameter of the driving pulley is 0.35 meters, so the radius is half of that, 0.175 meters. So our radius is 0.175 meters. That evaluates the linear velocity in meters per second. We can then determine the centrifugal tension, Tc, knowing the mass per unit length given in the question, having just calculated the value of linear velocity. We can evaluate Tc, 82.74 newtons in this case. To evaluate the effective driving tension for our formula, that's Tt minus Tc. We know that the maximum belt side tension Tmax is 800 newtons given in the question. We just evaluated Tc. Effective driving tension, Tt minus Tc here. I just note for reference, the Tc to Tt ratio is actually 0.1 here. For maximum power transmission conditions, we know from part 2 of our lecture series, that would have to be 1/3 or 0.3 recurring. So for the initial part of question 5, we are not operating at the optimum conditions for maximum power. That actually is the second part of the question. Question 5, the solution continued. So now we're able to determine the power transmitted per belt for the original conditions stated in the question. So here's our equation for power. Tt minus Tc is our T effective value. And then 1 minus e to the negative mu theta multiplied by cosec beta, all multiplied by the linear velocity of the belt. As we noted previously, don't forget that cosec beta is the same as 1 upon sine beta, so that's 1 upon sine 20 degrees in this case. I'll let you work through the arithmetic here, but essentially the power from one belt is about 8.6 kilowatts. But don't forget we have 4 belts, so the total power transmitted for the first part of the question is 34.3 kilowatts. So for the second part of the question, we now have to consider the optimum condition, and the optimum condition occurs when the centrifugal tension Tc is 1/3 of the total tension Tt. So Tc in this case is 800 divided by 3, so 267 newtons. That's the value of the centrifugal tension when we have optimum power conditions. So question 5, solution continued. I'll let you work through these calculations on your own. They're very similar to that previously undertaken in the first part of question 5. But now we're using the formula for maximum power from our summary on the previous slide. Pmax is 2/3 of Tt multiplied by the 1 minus e to the negative mu theta cosec beta, all multiplied by v. What we find now is for optimum conditions, the maximum power transmitted by one belt is 11.4 kilowatts. We have 4 belts to consider, so the maximum power transmitted 4 times 11.4, that's 45.6 kilowatts. Finally, we're asked to determine the percentage increase in power. So the formula is going to be Pmax for optimum conditions minus the P from the original specification in the question divided by the original P times by 100. Inserting the powers, the increase in power transmitted at optimum conditions is 33%, that of the original condition specified in the question. Let's consider question 6 from our notes. A belt drive consists of 2 pulleys labelled A and B, the centres of which are 4 meters apart. Pulley A has a diameter of 1 meter, pulley B diameter of 0.5 meters. When the belt drive is at rest, it's stationary, the tension in the belt is 0.7 kilonewtons. Assuming that the belt obeys Hooke's law, we have to calculate the tensions in the 2 portions of the belt between the pulleys when 1500 watts of power is being transmitted and the speed of pulley A is 3 revolutions per second. In this particular case, we're asked to ignore centrifugal effects, so no CF effects. In the bracket here are the answers for the tight side and the slack side tensions. So let's consider our summary of formulae relating to flat belt drives. I've assumed flat belt drives here as no groove angle is stated in the question. So what information are we given in the question? Well, we're given the power transmitted, P. There's another equation here for power, but I notice in the question we're not given the coefficient of friction, so I'm going to ignore this equation. I don't think we'll be using this equation for power. We're not going to be using this equation for power either, because again no friction coefficient stated, but also centrifugal effects are to be ignored, so there's no Tc value to consider. So I can rule out these equations from our analysis at the moment, and also this equation because no friction coefficient is given. So the power equation I think I'll be using initially will be this one. So what else am I given in the question? I'm given the initial belt tension T0, because we're informed what the tension is when the belt drive is at rest or stationary. I'm also given the dimensions of pulley A and pulley B, So I have the diameters, I have the radii also if I need that. I'm given the angular velocity of pulley A, so I could find the linear velocity of the belts, which don't forget is assumed to be the same on both pulley A and pulley B. The angular velocities omega A and omega B are different, but the linear belt speed is assumed to be the same, both pulleys. And just note for a point of clarity here, I'm using the term angular velocity, but to be correct, these are actually angular speeds of the pulleys because we're not actually given a direction of rotation in the question. I'm assuming direction of rotation. So I'm using the term angular velocity slightly loosely here. I just wanted to clarify that point. So in my equation, I think I can find v, linear velocity. So that's all the information extracted from the question. What am I trying to find? I'm trying to find the belt tension. So I need the maximum belt tension TT. That's a tight side tension. And I also need the slack side tension TS. So this is looking to me like a problem where I'm actually going to solve simultaneous equations. So I think I'll be using this equation here and solving it simultaneously with this equation here. That's my plan of attack to solve for the belt tensions. If you think you can attempt the question from here without further assistance, I'd encourage you to start the presentation and do so, but I'll show you the full work solution on the following slides. Here's question 6, commencement of the solution. So it's my pulley A, 1 meter diameter, pulley B, 0.5 meters diameter. My center distance, 4 meters between the pulleys. We're given the initial belt tension, 0.7 kilonewtons, so that's 700 newtons. And we're given the power transmitted, which is 1500 watts. Question 6, solution continued. So first of all, calculate the angular velocity of the larger pulley, that's pulley A, and here. We know from the question it's rotating at 3 revs per second, converted that into radians per second here, omega A, 18.85 radians per second. And now we can calculate the angular velocity of the smaller pulley using the equation omega B multiplied by diameter B. So omega A multiplied by diameter A. That's this equation here effectively. And I'm going to rearrange to find omega B. Inserting the values for omega A from above. For diameter A is 1 meter. Diameter B, which is 0.5 meters. We can evaluate omega A in radians per second. Question 6, solution continued. Now we can find the linear velocity of pulley A from V is equal to omega R. So inserting the values for the pulley A speed, pulley A radius, find the linear velocity. And all I've done on the next line is just check that value using the speed of pulley B and the radius of pulley B. And of course we should get exactly the same speed for linear velocity because the assumption made is that there's no slip or creep. So the linear velocity on the periphery of pulley A is the same as the linear velocity on the periphery of pulley B. So question 6, solution continued. So extracting the power equation from our summary of formulae, and this power equation ignores friction effects. This is the equation here. All I've done in the next line is divide both sides by V, so TT minus TS is equal to P divided by V. I've called that equation 1. I've also extracted this equation from our formula sheet. That's this equation here. And I've rearranged that for TS. In other words, subtracted TT from both sides of the equation. Call that equation 2. Question 6, solution continued. So now I'm going to substitute equation 2 from the previous slide into equation 1 from the previous slide. So there's equation 2 being inserted into equation 1. And the rest of it is algebraic manipulation, which I'll let you work through at your own pace. We'll eventually find is that the tight side tension is 780 newtons. Question 6, solution continued. Just repeated equation 2 from the previous slide and also the value of TT calculated on the previous slide. So then using equation 2, We can substitute the value of Tt into the equation here, and we can solve for Ts. And Ts was 620 newtons. So there's a solution for question 6. I will leave you with question 7 to review at your own pace. We have to calculate the power that can be transmitted by the belt drive, given the parameters above, and also determine the initial belt tension required. Answers shown in the bracket. Note this is a vee-belt problem, so if it helps you structure your solution, here's a summary of the formulae relating to vee-belts. Again, as always, I suggest you tick off parameters that you know from the question and then see if you can manipulate the appropriate equations to solve the problem. Note that centrifugal effects are to be considered in question 7. Here's question 8 for your attention. Again, I'll let you review this at your own pace. Note in this case is a flat belt drive, has no V-groove angle is stated here, and we're also informed to ignore centrifugal effects. Note we're asked to calculate an original coefficient of friction, given the information in the question, and a revised angle of lap. Answer shown in the bracket here. A slightly more thought-provoking question, but again, one I will leave you to attempt at your own pace. If it helps, here again is the summary related to flat belt drives. I would suggest that this equation might be useful in the solution, and it may need some rearrangement to find the friction coefficient mu. And here's question 9. This actually relates very much to the example 5 we commenced this presentation with. We've got to determine the least number of complete turns of the rope around the capstan or the drum, and the answer is shown here in the bracket. And here's the bibliography used to help generate this presentation, which I hope has been of interest to you, and as always, thank you for viewing.